Welcome to the Problems Channel Season 2, Episode 39, the episode which I titled Heron's Formula, Divided and Conquered, because in this episode we will discuss two distinct proofs of the Heron's formula that connects the area of every Euclidean triangle with its semi-perimeter, based on the divide and conquer problem-solving approach. Before we do that, however, as a traditional reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence and welcome to our channel. And second of all, it is a good idea for you to go to the homepage of this channel and in the channel's trailer section, find the episode titled The Problems Channel How To. Watch that episode in its entirety, follow all the instructions that were given in that episode, because in that episode we explain and motivate everything that we do on this channel. In the mathematical problem S2E39, we were asked to generate at least two distinct proofs of the Heron's formula based on the divide and conquer problem-solving approach, because that is the problem-solving approach that we're studying right now in a dedicated fashion. As a reminder, if A, B, C is a given Euclidean triangle, and if we name the lengths of the corresponding sides of the triangle as follows: against the appropriately named vertex of that triangle, we will put the side whose length is designated with the lowercase version of that vertex. For example, if uppercase A is the name of this vertex of the parent triangle, then the opposite side shown over here will be named with the lowercase a. If uppercase B is the name of this vertex of the parent triangle, then the opposite side shown over here will be named with the lowercase b. And lastly, if uppercase C is this vertex of the parent triangle, then the opposite to that vertex side shown over here will be named with the lowercase c. Moreover, if we agree that with the lowercase p we designate the semi-perimeter of the parent Euclidean triangle, which is basically a half sum of the length of the corresponding sides of that triangle, then the area designated with the uppercase S of this triangle ABC will be given as a square root that is extracted from the product of four factors: the semi-perimeter P itself and three factors that have the following shape: semi-perimeter P minus the length of the side of the parent triangle A, semi-perimeter P minus the length of the side of the triangle named B, times semi-perimeter P minus the length of the side of the triangle C. Now that we understand what needs to be done, let us look at the basic idea based on which our first proof will work. Our first proof of the Heron's formula will be based on the equality of the magnitudes of two angles generated by the InCircle of the parent triangle and an ExCircle of the parent triangle. We know that each and every Euclidean triangle possesses precisely and exactly one InCircle, and each and every Euclidean triangle possesses three distinct ExCircles. Out of these three distinct ExCircles, we only need one, and one such ExCircle in conjunction with the InCircle of the parent triangle will give us the competitive advantage. As such, in the upcoming diagram, please pay close attention to two angles named alpha over 2. In other words, alpha over 2 are the magnitudes of two angles to watch for in the upcoming diagram. That equality of the magnitudes of two angles generated by the InCircle of the parent triangle and an ExCircle of the parent triangle can be symbolized in a relation that captures the equality of two ratios. On one hand, on the one hand, we will have the ratio between the length of the radius of the incircle of the parent triangle to the distance between the points A and D. And do not worry, we will discuss this in great detail. You will understand what it means. And on the other hand, the ratio between the distance between the points A and E and the length of the radius of the ExCircle that is externally tangent to the side of the triangle, which we designate with the letter B, and that is why there is a subscript of B that is attached to the length of that radius. And now that we understand the nature of this key relation, we can develop our battle plan. As such, our battle plan will be the following one. At first, using the divide and conquer problem solving approach, we will prove that the area of the parent Euclidean triangle ABC can be expressed as the product between the length of the in radius of that triangle and the semi-perimeter of that triangle. In other words, in symbols, we'll prove that S is equal to the product of R and P, the length of the in radius, the magnitude of the semi-perimeter. That's on the one hand. This will take care of the numerator in this ratio. Then we will prove that the same length, the same area of the triangle S can be expressed in terms of the length of the the radius of the ExCircle as follows: P minus B. In other words, we will show that the area of the parent Euclidean triangle ABC can be expressed as the product of the length of the radius of the ExCircle of one of the ExCircles of that triangle, and the product of the difference between the semi-perimeter and the length of the side B of the triangle, and the side B is precisely the side to which this particular ExCircle is externally tangent to. This will take care of this denominator in this ratio. Then we will show, again, we will prove that formula using the divide and conquer problem solving approach. Then still using the divide and conquer problem solving approach, we will show that this distance over here between the points A and D, and I'll show you what the point D is, can be given as what? Can be given as a function, a certain function of the semi-perimeter P. In other words, we will express this length in terms of the semi-perimeter of the parent triangle. And also using the divide and conquer problem solving approach, we will prove that the distance between the points A and E in the numerator of the right hand side ratio over here is a certain function of semi-perimeter P. And once we have nothing but the length of the in radius of the parent circle, the length of the ExCircle of the parent triangle that is externally tangent to the side of that triangle named B, and we will have nothing but the semi-perimeter and the lengths of the parent triangle A, B, and C. This key relation over here will unlock precisely a proof of the Heron's formula. To that end, let us first use the divide and conquer problem solving approach in order to prove that the area of the parent triangle ABC, area of the triangle ABC, can be expressed as the product between the lengths of the in radius of that triangle and its semi-perimeter. In this segment of this video, we will use the divide and conquer problem solving approach in order to prove that the area of each and every Euclidean triangle can be represented as the product of the length of the in radius of that triangle and its semi-perimeter. To that end, recall that if we want to apply the divide and conquer problem solving approach to the process of generating a solution or a proof of this or that mathematical problem, we should try to carry out the following 3 steps. First, we should try to divide a given whole into a number of smaller and simpler primitive parts. 2, we should solve each and every such primitive part. And 3, we should find a way to combine the solutions of all the primitive parts into a solution of the whole. Of course, in real time, every time we look at a particular problem, it's not really clear, maybe sometimes right away, what is a whole, what is a primitive part, and such comes a challenge of seeing or identifying what can be a whole, what can be a smaller and simpler primitive part, how to solve a smaller and simpler primitive part. And then usually it's also quite a challenge to find a way to combine the solutions of the primitive parts into a solution of the whole. In this case, if you were solving this problem on your own, how would you apply the divide and conquer problem solving approach to a proof that the area of every Euclidean triangle can be expressed as the product of the length of the in radius of that circle and its semi-perimeter? Well, here is one way. For a whole, it makes sense to take the entire parent triangle ABC. And then what could be the smaller and simpler primitive parts? The smaller and simpler primitive parts could be 3 smaller triangles that tile or partition the area of the given parent triangle ABC tight with no gaps and overlaps in such a way that the vertices of these smaller 3 triangles are the vertices of the parent triangle A, B, and C, and all these 3 triangles share one and the same common vertex whose role is played by what? Whose role is played precisely by the center of the inscribed circle of that triangle. We remember that each and every Euclidean triangle possesses precisely one unique InCircle. And how do we find the location of the incenter? Well, in this case, it doesn't really matter much for us, but the center of the InCircle of each and every Euclidean triangle is located at the intersection of the interior angles of that triangle, and that point is shown over here, O, right here. Consequently, our smaller triangles become A, O, B, hatched over here in red at the bottom, B, O, C, hatched on your left hand side with blue, and C, O, A, hatched on your right hand side with yellow. And now, once we carry it out, it looks like the first step and kind of the second step of the divide and conquer problem solving approach. We identified the whole, the Euclidean triangle ABC. We identified the smaller and simpler or primitive parts, the triangles that are constructed on the center of the inscribed circle of that triangle as their common or shared vertex. Now, how do we solve each primitive part? Well, the solution of each primitive part, in this case, amounts to finding the area of each such smaller triangle. Now, in symbols, we could write the following. We can write that the triangle ABC can be represented as the union of the triangles. Which ones did we say? The triangle AOB unionized with the triangle BOC, triangle BOC, which is unionized with the triangle COA, triangle COA. And if we throw more symbols at it, for example, we can write that the area that, the triangle itself will designate the parent triangle as tau, can be represented as the union of the smaller triangles where I runs from 1 to 3. This is a somewhat grown up notation, do not worry about it. But now, how do we carry out the last step of the divide and conquer problem solving approach? Find a way to combine the solutions of all the primitive parts into a solution of a whole. Well, the way The third step in this case is amazingly enough natural. It's actually driven by this idea over here. Once we partition the whole into a union of subparts, then evidently, what can we say about the interesting metric in this case, which is what? The area. The area is the interesting metric. Well, we can say that the area of the parent triangle can be represented what? Can be represented as the sum of the areas of the smaller triangles, where these guys vary. The index I varies from 1 to 3, so we have 1, 2, 3. Name the smaller triangles tau 1, tau 2, tau 3. Tau is the whole thing, and thus comes out this observation. So now let us combine all that work into one neat package, and we shall write what? The area of the parent triangle ABC can be expressed as the sum of the areas of the smaller and simpler or primitive triangle that tile or partition the parent triangle, tight with no gaps and no overlaps. Now observe over here the utility of choosing the InCircle for this particular material in this problem. The in radius in all three cases shown, for example, here, and here, play the roles of what? Each such in radius plays the role of the height of the corresponding smaller and simpler primitive part. In other words, for the area of the triangle AOB, what do we have? It's the half product of the length C times the length of the in radius R. For the area of the triangle BOC, what do we have? It's a half product of the length of the side A times the radius R. And for the area of the triangle COA, what do we have? It's a half product of the length of the side B times the length of the in radius R. And what do we see? We see that precisely the length of the in radius R factors into each summed in the same power, in the same way. The first power, positive power, that means that can be factored out. And what can we write for this formula then? It will be the length of the in radius times the lengths of the sides A plus B plus C over 2. And look at the magic. What do we have over here according to our convention that we agreed on in the earlier segments? This part right here is precisely the magnitude of the semi-perimeter of the parent triangle ABC. And thus, out comes our claim that the area of each and every Euclidean triangle ABC is or can be expressed as the product between the lengths of the in radius of that triangle and its semi-perimeter P. Now that we understand how the divide and conquer problem solving approach was applied to the proof of that fact, again, one more time, we suggest that you put this video on pause, walk away, reconcile in your mind all the steps that we did. But again, remember, the steps at the 1,000-foot view or at the bird's eye view are the following. Divide, solve, combine. Divide the whole into smaller and simpler primitive parts. This time the parts were smaller triangles that tile the area of the parent triangle. The solution of each part amounts to representation of the area of that triangle through the material that we have at hand, the length of the in radius and the length of the corresponding side ABC, and find a way to combine the solutions of all the primitive parts into a solution of the whole. Comes down actually from our very first observation of tiling tight with no gaps or no overlaps or partitioning, and thus comes the proof. Now that we understand how that proof worked, let us prove the next fact, that the area of the same parent Euclidean triangle ABC can be expressed through the length of the radius of 1 out of 3 possible ExCircles of that triangle. And we showed that formula before. We'll prove in the next segment that the area of the triangle ABC can be represented as the product of the length of the radius of an ExCircle that is externally tangent to the side of the parent triangle of length b, and the difference between the semi-perimeter and that length b. This is what we will prove in the next segment using the divide and conquer problem-solving approach. Wonderful. In this segment of our video, we will use the divide and conquer problem-solving approach in order to show that the area of each and every Euclidean triangle can be expressed in terms of the length of the radius of one of its ExCircles, shown over here as RB, and the length, the size of, or the magnitude of its semi-perimeter P, as shown over here in the upper hand side of your screen. So again, how can we apply the divide and conquer problem-solving approach to the process of generating a proof of this statement shown over here? Well, first of all, let us recall our early agreement that if uppercase A, uppercase B, and uppercase C are the names of the vertices of the given Euclidean triangle, then we name the sides of that triangle with the corresponding lowercase letter for the side that lies opposite to the uppercase version of that letter. In other words, if the uppercase A, uppercase B, and uppercase C are the names of the vertices of our triangle ABC, then the sides and the lengths of the corresponding sides will be B, because this side lies opposite the vertex B, A, because this side lies opposite to the vertex uppercase A, and lowercase c, because this side lies opposite to this vertex with the name uppercase C. Then how do we construct an ExCircle of that triangle that is externally tangent to the side, let's say B, shown over here on your right side of the parent triangle ABC? Well, by definition, that center of the ExCircle, which we will name sigma B, will be what? It must be equally distant from the extensions of the sides, in this case C and A, and it must be also equally distant from the side B. Consequently, the center OB of that ExCircle sigma B will be located where? At the intersection of the angular bisectors of the external angle at A, external angle at C, shown over here, and I did not show it yet, we'll use it in the next few minutes, the interior, the bisector of the interior angle at B, which runs this way, and all these three bisectors intersect at one point. This is the center of the ExCircle of the parent triangle that is tangent to the side over here, in this case side B. Consequently, when we construct, all these constructions can be carried out with the traditional Euclidean tools of a straight edge and a compass. Once we locate that point OB, we construct a perpendicular to any of the extensions C or A, side CA, or directly drop a perpendicular on the side B, and thus obtain the length of the radius RB of the ExCircle in this case. So now, if we want to prove this relation shown on the upper right hand side of your monitor using the divide and conquer problem solving approach, how can we do that? Well, remember again, divide, solve, find a way to combine. So what can be a whole in this case? Well, my idea is that in this case, the whole can be what? The whole can be the quadrilateral A, B, C, OB. You see, we bring in the center of the ExCircle sigma B into the game over here. In other words, we will write that the quadrilateral A, B, C, OB can be represented which way? Here, the process of application of the divide and conquer problem solving approach to the process of generating the proof of this relation is a slightly more nuanced with respect to how we did it in the previous segment. Here, first, on the one hand, we represent that whole as the union of which two triangles? Here we represent our new whole as the union of the triangles A, B, C. The triangle A, B, C. And what else? And the triangle A, C, O, B. A, C, and O, B. And what does that maneuver by us? In other words, our whole, smaller and simpler primitive parts. Step number one, divide the whole into a number of smaller and simpler primitive parts. Now solve each part. What does solve each part mean in this case? The solution of each part in this case means writing down or representing the interesting metric again, or the area of the triangles, in terms of the locally available material. What is the area of the, let's say, the area of the equilateral A, B, C, and OB is? What is this area? Well, from the tight tiling, no gaps and no overlaps, or in mathematics it's called partitioning of the whole into subparts, or a set into subsets, can be represented how? Through the area. So the area of the parent triangle ABC is precisely S of the triangle ABC, and this is the material that we're looking for over here in this formula. That is what we're shooting for. Plus, we translate the union into the plus. What? The area of the triangle, the area of the triangle ACOB. What can we say now once we make this observation? And this is our second part of the divide and conquer problem solving approach, where we're trying to solve each part. The solution of the first smaller and simple primitive part is what? Is the letter S, the area of the parent triangle ABC that we're looking to express as the product shown over here. And what is the solution of the second smaller and simpler primitive part? The solution of the second smaller and simpler primitive part is the area of the triangle ACOB. And what is the area of that triangle? Well, it's a half product of the base, which is letter played by the side B, and what? And the height. And what is the height of the triangle ACOB? The height of the triangle ACOB is precisely the length of the radius of the ExCircle sigma B, as we constructed it in the previous steps. So thus we write, this will be area of the triangle ABC plus half product of what? The length of the side B and the radius of the ExCircle, the length of the radius RB. This is our first observation. What is our second observation? Well, the second observation is, again, we will apply the same divide and conquer problem solving approach for the third time already in this episode, by partitioning the area of the quadrilateral ABCOB in yet a different way. And what is that way? Well, we will partition that quadrilateral as follows, by constructing exactly the line that plays the role of the bisector of the interior angle at B. You see, like this. And now, what will we have? Let me grab green and blue. And now we partition that quadrilateral as a union of what? As the union of the triangle, let's say BCOB, this triangle. I'll hatch it in blue. This triangle. And BAOB, and this guy. Let's say I'll hatch it in green. And this triangle. And this triangle that runs this way. In other words, we will write right now as the union of what? Let's say this way. The triangle BCOB BCOB unionized with which triangle? BAOB. BAOB. And that means that the same area will again apply the same idea, that the area of the quadrilateral ABCOB, it can be represented as the sum, straightforward arithmetic sum of the areas of two smaller and simpler primitive parts. Again, I may not be saying these words all the time, but you guys should not be lazy and say these words. The whole in this case is the quadrilateral ABCOB. The smaller and simpler or primitive parts, the triangles BCOB and BAOB. The solution of each and every smaller and simpler primitive parts amounts to the expression of the area of these two triangles in terms of the available material, which is what? Now let's think carefully. The base of the triangle BCOB can be played by what? Precisely, the base of the triangle can be played by the side A. And in this case, what will be the height of the triangle? Exactly, the height of that triangle will be yet another incarnation of the radius RB that is shown over here. I'll write it over here as the same radius that falls perpendicularly from the center of the ExCircle, sigma B from the point OB, onto the side BC extended, and that is the height. So what will be the answer here? 1/2 of A times RB, where RB is the length of the radius of the ExCircle sigma B. Likewise, when we want to solve the triangle BAOB, which means that we want to write down the expression for the area of the triangle in terms of the local material, that expression will be what? Half product of the base, which will be what? The side C shown over here. And what else? Precisely, the role of a height of the triangle that emanates from the vertex OB will be played by what again? It will be played again by this here line segment, which is another incarnation of the length of the radius of the ExCircle sigma B. It's another orthogonal, officially orthogonal projection of the point OB on the side BA extended. So here we will write plus 1/2 what? C times RB. Now what do we have? We can write down the expression. We can throw out, you see at this point, the auxiliary quadrilateral ABCOB played its purpose. It outlived its usefulness for us. We throw it out, we forget it, and now we work precisely with this. And again, this part right here represents what? This part, this sum right here. This part over here represents the symbolization of the third step of the divide and conquer problem solving approach. Find a way to combine all the solutions of all the primitive parts into a solution of the whole. So now we simply write down the expression for the area of the triangle ABC in terms of what? Again, the length of the radius RB of the ExCircle sigma B can be factored out. It is entered into this relation uniformly all over, and this will be what? 1/2 of what? The length RB times, let us carefully construct, A plus C, A plus C. Now what will happen over here? This guy will jump over the equal sign to the right hand side, and the B will be here with the minus sign. But if we have A plus C, our semi-perimeter is what? Is the half sum of the lengths of the sides of the triangle A, B, and C. What is missing over here? What's missing over here is B. And if we added it, we must subtract it. And once we subtracted B minus B is 0, we did not really alter the magnitude of that sum. Plus we have another B over here, minus. And what do we have? This over here in conjunction with 1/2 will be precisely P. and minus b, and minus b will be what? Minus 2b. 2b over 2 will be precisely b. And thus, what we have is exactly our expression. The length of the radius rb of the ExCircle sigma b times the semi-perimeter pa plus c plus b over 2. And now, from this, we subtract what? Minus b minus 2b over 2 minus b. And voila, problem solved. Proof is generated. The area of the triangle ABC, just like we claimed over here on the upper right hand side of your screen. Now we carried out, remember, we go back to our battle plan. We had 4 steps. We carried out 2 steps. We proved that the area of the parent triangle expressed in terms of the length of the radius of the InCircle is blah. We now prove that the same area of the parent triangle ABC can be represented as the product of the length of the radius of the ExCircle sigma b and the difference between the semi-perimeter and the corresponding length of the side B, shown over here. And now we need to go back and pay slightly more attention to the key relationship. Remember, I will take a break right now, erase the board, and prepare it for the next segment. While I do that, you guys think about this. What I will draw next, it will be the InCircle over here. And remember, this angle right here, this angle. And we will have this angle right here. You see? How do these two angles are how do these angles are connected, and what can we say about their magnitude? That is the question that we will answer in the next segment. Excellent. In this segment of this episode, we will show the key relation around which the entire proof of the Heron's formula is built. In other words, in this segment, we will show that the magnitude of the angle AOBE is precisely the same as the magnitude of the angle OAD. But first, let us decipher what is going on over here and what does this diagram mean. We begin with our parent Euclidean triangle ABC with the sides A, B, not shown over here to avoid the clutter, but this side is B, and this side C. Next, working with the parent triangle, we inscribe the circle into it, just like we did it in our earlier segment. And where is the center of the InCircle of each and every Euclidean triangle is located? The center of each, the center of the InCircle of each and every Euclidean triangle is located at the intersection of the angular bisectors of the angles of the parent triangle. A, B is the internal bisectors of the interior angles. And we also agree over here to name that point, the center of the InCircle, as O. And next we project the center of the InCircle O onto the side BA, or onto the side which we named with the lowercase c, orthogonally. And that orthogonal projection of the incenter O onto the side BA we named the letter D, which is exactly what I used in the opening segments of this episode. So far so good. Now, the thing that we need to know here is that we connect the center of the InCircle O with the vertex A, with this line segment. And this is basically, or we have it as a side effect, because remember, this point is located at the intersection of the angular bisector of the interior angles of the parent triangle. Consequently, as I wrote over here, the magnitude of the angle CAB will be alpha. And precisely because of the mechanics of how the incenter is located for our parent triangle ABC, we have it that the magnitude of the angle OAD the magnitude of the angle OAD is precisely what? The OA is a part of the angular bisector of the interior angle at A. It means that the magnitude of the angle OAD is precisely 1/2 of the angle CAB over here. I marked it as alpha over 2. Now we step to the ExCircle. This is the side A of the parent triangle, this is the side C, this is the side B. I do not write the letter B to avoid the clutter, but we understand this is the side of the triangle to which we refer as lowercase b. Externally to that side B, we construct a circle that also touches the sides BA and BC extended. We know that the center of that ExCircle, sigma B, or the point OB, is located where? At the intersection of the angular bisectors of the exterior angles at A and at C, and of the angular bisector of the interior angle at B, not shown over here. Next, we do the same thing. We take the center OB of the ExCircle sigma B and we project it on the side BA extended orthogonally into the point E. In other words, the angle OD, let's say B or ODA, is right, pi over 2 or 90 degrees, and the angle OEA, for example, OEA is also right, pi over 2 or 90 degrees. And what else should we remember? Precisely when we connect the point OB with the vertex A, we get what? We get the angular bisector of the angle EAC, and that means that the magnitude of the angle EAOB, this angle right here, is what? Is the same as the magnitude of the angle CAOB, this guy right here. So these angles are of the same magnitude. So now the angle OBEA is pi over 2, as I wrote over here to capture this fact. And now we engage in the process, which in Olympic math is called angle chasing, but it's not really that complicated. We begin with the triangle, which one? AEOB. So with the triangle, let's write it down here, the triangle AEOB, and for that triangle we write what? This is one of the Euclid's elements propositions in his first book. The magnitudes of the interior angles of each and every Euclidean triangle sum to pi radians, or 180 degrees. The angle x plus the interior angle at E plus the magnitude of the interior angle at A is basically pi, and that is what we write down. X plus the magnitude of the angle at interior angle at E, which is pi over 2, plus pi over 2, plus what? Plus the magnitude of the angle EAOB. I will skip it for now for the reasons that we will understand in a minute. And this is all equal to pi. Now the magnitude of the angle EAOB is what? EAOB, the magnitude of the angle EAOB is equal to the magnitude of the angle CAOB. That means that is precisely 1/2. This angle is precisely 1/2 of the angle CAE or EAC. So let us write it down. The 1/2 of the angle, which one? EAC over 2. The magnitude of the angle EAC over 2. It's this guy, basically. This guy. And now, what do? Well, we have the connection. The angle EAC, the angle EAC, shown over here, plays what role? It's the exterior angle with respect to what? To our parent triangle, ABC. So in this vertex right here, at this angle, we have interesting things happen. What are these interesting things? Well, we see that the complete angle over here, let's call it BAE, is pi radians, right? Pi radians. And that angle is what? The angle E, the magnitude of the angle EAC, the magnitude of the angle EAC, this is precisely what we have here, plus the magnitude of the angle CAB, which is what? Which is alpha, plus alpha. In other words, this angle right here, this whole thing, this whole angle is pi radians, and we represent it as a composite quantity. In some sense, if you wish, that's another application of the divide and conquer. What's the whole? The angle, the straight angle, PAE, the pi radians. What are its two primitive parts? The magnitude of the angle EAC plus the magnitude of the angle CAB. The solution of each part is what? Is simply writing it down and combining it into a sum, and voila, here we have it. So now let's rewrite this formula over here with this observation at hand. So what will we have? X plus pi over 2 plus the magnitude of the angle EAC divided by 2, which is what? Pi minus alpha over 2, and all this beautiful mess is equal to what? It's equal to pi radians. Again, courtesy of Euclid's Elements, Book 1, proposition, I don't remember exactly, you guys can look it up, 18 or 21 or some such. So now all we have to do is this. Spell it out. X plus pi over 2 plus another pi over 2 minus alpha over 2 equals 2 pi. You see, split this ratio into two fractions, pi over 2 minus alpha over 2. Now, what is going on here? Pi over 2, and this pi cancel each other out. And what do we have? X minus alpha over 2 equals to 0. In other words, x is equal to alpha over 2 precisely. This is exactly what we wanted to show, and this is what we opened this episode with. The magnitude of the interior angle at the point O, at the center of the ExCircle, this guy, is equal precisely to the magnitude of this angle right here. And this angle over here, alpha over 2, is generated by what? This angle is generated by the InCircle, which is unique. And this angle right here is generated by what? That angle is generated by an ExCircle of the given Euclidean triangle, of which each such triangle has how many? Exactly 3, but we work with 1. It's enough to work with 1. You can work with any other one, and exactly the same result will follow. But now, this is the important result that we proved. And remember that in our battle plan, we had 4 steps. First step, we proved this relation using the divide and conquer problem solving approach. Using the same divide and conquer problem solving approach, in the second step, we proved this relation over here. And now we can capitalize on the equality of the magnitudes of these two angles. Which way? Well, we can bring in Euclid's Elements, Book 6, Proposition 4. In his Elements, in Book 6, let me write it down where I can write over here, guys. Just check this out. Book 6, Proposition 4. Euclid's Elements, Book 6, Proposition 4. Euclid uses a somewhat funny, by modern standards, language when he says that in equiangular triangles, the sides about equal angles are in the same proportion where the corresponding sides are opposite equal angles. What does it mean? In modern times, if you tell some student of mathematics that two triangles are equiangular, that student will most likely think that the triangles are equilateral, 60 degrees or pi over 3 radians for the magnitude of the interior angles. That is not the case. In a slightly more modernized tongue, we will say that according to the Book 6, Proposition 4, In similar triangles, the lengths of these triangles that subtend the same angle by magnitude are in the same proportion where the corresponding sides lie opposite equal angles. What does that mean? Well, we already showed that the magnitude of the angle x, or the magnitude of the angle AOBE, is exactly the same as the magnitude of the angle OAD, alpha over 2, alpha over 2, just to give a designation. With alpha, remember, we steal from Latin the uppercase letters, and we steal from Greek the lowercase letters. So the vertex A is married with the interior angle alpha, the vertex B is married with the interior angle beta, and the vertex C married with the interior angle gamma. Alpha for the entire angle, half of it alpha over 2, there we go. So now we proved, what did we prove? We proved that the triangles, let's mark these guys, this triangle over here and this triangle over here, these two triangles are what? They are similar. So from the similarity, and I will write it, the names of this triangle in such a way that the vertex of that triangle that is attached to the magnitude of pi over 2 or 90 degrees sits dead in the middle. Now these triangles ODA, triangle ODA, and remember at the vertex D we have a 90-degree angle of pi over 2, and the triangle AEOB and the triangle AEOB, AEOB, this one with the magnitude of the interior angle at E, and E sets dead in the middle of the name, is pi over 2 radians, 90 degrees. These two triangles are what? Well, first of all, these two triangles are right by construction. We took each corresponding center, in center, and one of the x centers, projected these centers orthogonally on the side BA and BA extended, obtained right triangles, and we proved that the remaining, these angles over here, are the same by magnitude. And what does that mean? By the corresponding proposition from Euclid's Elements from book 1, the remaining angles, like this guy and correspondingly which one, and this guy, must be the same. Thus these triangles are similar, and precisely by book 6 proposition 4, the lengths of the sides of similar triangles that subtend one and the same angle of the same magnitude are in the same proportion when these sides lie opposite equal angles. What does it mean? Well, from the triangle, this one, ODA, what do we write? We take the side R, which is the side OD, which represents what? The length of the radius of the InCircle. Construct the ratio of R to what? To the distance between the points A and D, this side to this side. AD, like so. And from this triangle, from the triangle AEOB, what is the equivalent of the side OD in this triangle? Well, the side OD in the triangle ODA lies opposite to which angle? Alpha over 2. Where is the angle alpha over 2 in the triangle AEOB? Is this guy right here. So opposite this angle lies which side? Side AE. So we write down the distance between the points A and E is in the same proportion to what? The side DA in the triangle ODA lies opposite to this angle right here. And what is the magnitude of this angle in this triangle AEOB? It's this guy right here. So here we take this side in this triangle, and that is what? That is precisely the length of the radius of the ExCircle that is externally tangent to the side B, which is marked as RB. And voila, by book 6 proposition 4, these two ratios must be the same. This is the organic understanding of what is going on without bringing the more modern trigonometric function of tangent. Book 6 proposition 4. And now we carried out, remember, the first step of our battle plan, the second step of our battle plan. Now we know how to express r in terms of the length of the in radius r in terms of the area of the parent triangle and its semi-perimeter. We know how to express the length of the radius of the ExCircle sigma b in terms of the semi-perimeter and the length of the corresponding side b. What do we have to do now? Remember, we need to show that the length of the side AD is a certain function of semi-perimeter, and the length AE, or the distance between the points A and E, is also a certain function of the semi-perimeter P. And that is exactly what we will do. Again, piecemeal, we will start with the distance between the points A and D first. Very good. Now that I erased the material that you guys keep track of in your records nicely, I moved it over here, the ratio that we proved. The length of the inner radius to the distance between the points A and D is the same as the ratio of the distance between the points A and E, and the length of the ExCircle constructed externally tangent to the side B, centered at OB, to which we refer sigma B. And now in this segment we will prove that the distance AD, the distance between the points A and D, is actually a linear function in the semi-perimeter of the triangle ABC, of the parent triangle ABC. How will we do that? We will do that again for demonstration and illustrative purposes using the divide and conquer problem solving approach. Again, remember, divide, solve, combine. Divide the whole into a number of smaller and simpler primitive parts. Solve each and every primitive part. Find a way to combine the solutions of all the primitive parts into a solution of the whole. What is the whole over here? The whole in this case will be the entire perimeter, all the sides of the triangle ABC. What are the parts? Well, let us do this. Remember that we took, in the previous segments, we took the in-center O of the triangle ABC, projected it orthogonally onto the side C, obtained the point D. Now we do the same thing, the same operation, and project the point O, the in-center, onto the sides A, and obtain the point G. Let's name it the point G over here, this point G. And when we project the in-center O onto the side B, which I do not show to avoid the clutter, we'll obtain the point, we'll call it F. So now what are the smaller and simpler primitive parts? Well, now we go back to the wonderful theorem that Euclid proves in one of his, I think it's the book 1. It has to do with the, let's do this. Let's say the point A. With respect to the InCircle, let's call this circle sigma O, for example, because it's center over here. With respect to the InCircle sigma O, what does it play? What role does it play? Well, it is a point that is external with respect to the InCircle sigma O, and the sides of the parent triangle AC and AB here play the role of external tangents constructed to one and the same fixed circle in the parent plane through one and the same fixed point A, and the lengths of these tangents are exactly the same. In other words, the length of the line segment AD, the length of the line segment AD is equal to precisely what? The line segment AF is equal to AF. So far so good. So don't forget that F is the orthogonal projection of the in-center O onto the side CA. And what else can we say? The same exactly things we can say about the line segments CG and CF. And BD, BG. Why? Because all the time the point B is external with respect to the InCircle sigma O, and the line segment BD is the external tangent drawn to one and the same circle through the same point, and the BG is also an external tangent. And the lengths of these segments are one and the same. I think in one of our previous episodes we actually prove it. If we did not, it's a good idea. It's a good exercise for you guys to go through and construct the helper triangles, and through the congruence of triangles prove that statement. Likewise, the length of the line segment CG is the same as the length of the line segment CF. And now what do we do? Well, we're interested in capturing these guys as a function of P. So this is exactly what we do. What is the length of the line segment AD, or the distance from the point A to the point D, in terms of the length of the side AB or the side C? Well, we write it down. The length AD is what? Is the length of the side C, which is C minus the length of what? Is the length of the line segment DB, or the distance between the points B and D, minus the points B and D. That's all there is to it. And now we keep rolling. C minus, this is lowercase c, guys. I know you guys complain about me writing too small and too illegible. So here, A and D, uppercase C is lowercase, not the point C, not the vertex C, not this guy. Not this guy. It is this guy, the length of the line of the side AB. So lowercase c, lowercase c. Now, the distance between the points B and D is the same as the distance between the points B and G, because these distances, like we said, are the parts of the tangents drawn to the same circle through the same fixed point. But the distance BG is what? In terms of the locally available material, it's the length of the side A minus, what do we subtract? The distance between the points C and G. So far so good. Minus C and G. Parentheses equal to, we keep rolling, C minus A, minus and minus plus. How do we express the distance between the points C and G in terms of the locally available material? The locally available material is the length of the side, so the distance from the point C to the point G is exactly the same as the distance from the point C to the point F. And what is the distance from the point C to point F can be expressed as the length of the side B minus the distance between the points F and A. I'll write it as AF, but C minus A plus B minus the distance between the points A and F is what? This is the external tangent to the circle sigma O in circle of the parent triangle ABC. It's the same as the length of the tangent AD. So the circle closes, so to speak, for instance, AD. And voila, we have AD on the left-hand side of the equal sign. We have AD on the right-hand side of the equal sign with opposite signs. So what does it mean? It means that 2 times the distance between the points AD is equal to C plus B minus A. So how do we manufacture the locally available material, the semi-perimeter P, using this bunch of symbols over here? Well, that is a trivial task. We do what? We add another copy of A, we subtract another copy of A. You see? C plus B minus A plus A minus A. We throw A, this copy of positive A, into the mix over here, and what do we have? 2 times the distance AD is equal to A plus B plus C minus negative A and negative A, 2 times A. So far so good. This maneuver is nothing more than the good old middle school symbolic shuffling. Divide both sides of the equation by 2, and what do we have? We have the distance between the points A and D equal to what? A plus B plus C over 2 is what? This is our favorite semi-perimeter, P, minus 2A over 2 minus A. Voila. We're almost home free. We're almost done. We now show that the distance between the points A and D, obtained as explained earlier, is basically a linear function in the semi-perimeter P. And we can now put the distance P minus A over here, express R as S over P, express RB as S over the difference over here, P minus B. And what do we have left? We just need to do the same thing with the distance between the points A and E. And this is exactly what we will do in the next segment. Very good. In the previous segment, by using the fact that the lengths of the external tangents drawn to one and the same circle through one and the same point equal one another, we show that the distance between the points A and D is equal to P minus A. P is the semi-perimeter of the parent Euclidean triangle ABC. And if we go through exactly the same exercise as we went through a few seconds ago by chasing down basically the lengths of these tangent line segments, we will prove that, for example, the distance between the points B and G, this distance right here, is P minus B, and this distance right here. We'll prove that the distance between the points C and G is P minus C right here, and this distance over here, I don't want to clutter it too much, but you understand. And the same thing, the distance from F to A and F to D is P minus A, and that's how you will construct the nice diagram that you saw that I showed to you guys before the beginning of the previous segment. And again, I did not spell out all the gory details about the how divide and conquer problem solving approach slayed this little problem over here, but actually we applied that problem solving approach anyway. The whole was the entire perimeter. The primitive, the smaller and simpler primitive parts were what? The line segments tangent to the InCircle, smaller one, the solution of which one was what? The fact that these smaller and simpler primitive parts or tangent line segments created or summed to the entire perimeter, and by chasing down this length, we came up with this expression over here. Exactly the same idea will work out right now when we will prove that the distance between the points A and E is actually also a linear function in P. And how will we do that? Well, in this case, in some sense, we can say we also will apply the divide and conquer problem solving approach. And again, what is the whole in this case? The whole in this case will be again the perimeter of the given triangle ABC and of the given Euclidean triangle ABC. And what are the smaller and simpler primitive parts? Well, this time, remember, in the previous segment, we projected the in-center onto the sides of the triangle. And here, when we work with the ExCircle, because we want to capture the distance between the points A and E, we do the same thing. We take our X center, or one of the X centers, the center of the ExCircle sigma B OB, and we project it onto the remaining sides. On the side A, BC extended into the point K. The line segment OK is orthogonal or perpendicular to the side of the triangle BC extended. And we project that point OB, the center of this ExCircle sigma B, onto the side AC into the point M. This is the guy M. This is the point. Again, right angle, pi over 2 radians, 90 degrees. Everything is wonderful. Now, what do we observe? What is the tactical fodder for our deduction? The fodder for the tactical material for our deduction is the following, exactly the same idea. The lengths of the tangent segments drawn to one and the same fixed circle through one and the same fixed point in the parent plane are one and the same. Here we look at the point B, concentrate on the point B over here. The line, the straight line, or the ray BE is what? Is a tangent, external tangent to our ExCircle sigma B. And the ray BK is also external tangent to the ExCircle sigma B. Consequently, the lengths of the line segments BE and BK are what? One and the same. We write it down. The distance between the points BE and BK is one and the same. That is the starting point. And now we go deep dive into divide and conquer. We now break our whole into parts. We solve each part and we combine the solution of each primitive part into a solution of the whole. How do we do that? Well, we're interested in this distance over here between the points A and E. How can we express, how can we splice that distance into our relation? Well, the distance between the points B and E can be represented what is a composite quantity. It's C plus AE. So we write down here C plus AE is equal to what? How do we represent BK, the distance between the points B and K? Well, it's the side A, A plus what? This is actually, by the way, we're going through the steps of the divide and conquer problem solving approach. Find a solution of each and every primitive parts. Our primitive parts now become the tangent line segment, tangent. So here we will say that the distance between the points B and K, this distance is A, for the distance between the points B and C plus the distance from the point C to the point K. However, what do we see? The distance from the point C to the point K must be the same as the distance from the point C to the point M, because these line segments are external tangents drawn to one and the same ExCircle through one and the same fixed point C. So this is what we write, CM plus the distance from the point C to the point M. However, the distance from the point C to the point M can be expressed with the locally available material in which way? Well, the distance between the points C and M can be expressed as the length of the side B. This is B minus the distance between the points A and M. A and M. But again, the point A with respect to the ExCircle sigma B is what? It is the point through which the tangents AE and AM are constructed. It means that the distance between the point A and M is the same as the distance between the points A and E. This is the same as the distance between the points A and E. And voila, let us roll it up into one beautiful equation. C plus the distance between the points A, E is equal to what? A plus B, A plus B minus AE. Now that you guys understand what's going on, I'll just erase this and I will write down AE. You all understand where did this magic come from. And now what do? Well, we collect all the AEs on the one side of the equal sign. We throw all the other material to the other side of the equal sign. What do we have? Two copies of the distance between the points A and E can be represented as A plus B minus C. Again, what do we do here? We need to splice our favorite semi-perimeter of the parent Euclidean triangle ABC into the right-hand side of the equal sign. How do we do that? We add one copy of C and we subtract one copy of C. You see? Minus C plus C minus C. This C comes over here. So now two copies of the distance between the points A and E is equal to A plus B plus C minus C and minus C minus 2 times C. So far so good. And what do we do now? We divide this result, the last equation, through uniformly by 2. The distance between the points A and E is equal to a plus b plus c over 2 is what? It's the classical definition of the semi-perimeter of the parent Euclidean triangle ABC, and 2 times c over 2 is c minus c. Voila! This is precisely what we wanted to prove. Now we have eliminated all the material but the interesting one, which is what? Basically semi-perimeter of the parent triangle ABC, which is again basically the length of the sides A, B, and C of that triangle. Now that we have all the pieces in hand, all the pieces at hand, we basically take them and slug them in to our relation over here that we already proved, and we will carry out this straightforward manipulation in the next segment. Now that in the previous segment we proved that the distance between the points A and E, the points A and E, is equal to the difference between the semi-perimeter P of the parent Euclidean triangle ABC and the length of its side C, we just basically plug in these results, all 4 results, into our main relationship that we deduced previously, and we carry out a straightforward computation. That manipulation will be very, very quick. Here is why. For the length of the in radius r, we have through this formula what? We have S over P. So far, so good. In the denominator of this ratio, on the left-hand side, we have the difference P minus A. So we write down P minus A. And that ratio is what? The distance between the points A and E, which is P minus C. Pi minus C divided by the length of the radius of the ExCircle RB over here. This length, or this length. We already have it from here, which is what? S, and here we need to multiply this by P minus B. P minus B. And this is it. Game over. Cross multiply. What do we have? S squared is equal to P times, let's say, in the same order, P minus A times P minus B times P minus C. And there we have it. Erase the square, extract the square root. All these quantities are strictly positive. Everything here is a real number. Problem solved. The Heron's formula proved using precisely the application of the divide and conquer problem solving approach. By my count, at least 6 times we did it. But you guys keep me honest, go over this episode one more time and verify. And now that we generated that proof based on the equality of the magnitudes of these 2 angles over here, we will show you the second proof of the Heron's formula that is also based on the divide and conquer problem solving approach, but which revolves strictly around the angles that are generated by the inscribed circle of Euclidean triangle. As I promised earlier, the second proof of the Heron's formula that uses the divide and conquer problem solving approach will be based solely on the angles that are generated by the InCircle of any Euclidean triangle. And again, remember that first and foremost, mathematics is a play of thought. If you were not able to generate the proof that we're about to show you, we suggest that you put this video on pause, walk away, think about it, because the hint is right here. Study the angles that are generated by the InCircle of any Euclidean triangle. Very well, now that you thought about it, the theorem that you either generated yourself back in middle school or you were asked to generate is the following. If the 3 real numbers x, y, z are such that they sum to pi, then the sum of the tangents of the trigonometric functions of tangent of the number x, of the number y, and of the number z, their sum equals to the product of these trigonometric functions evaluated at the angles x, y, and z. In other words, sum of the trigonometric, or sum of the values of the trigonometric function of tangent, is equal to the product of these very values of the very same trigonometric functions of tangent evaluated at the angles x, y, and z. This is the second hint, as we explained in season 1, episode 2. It is a good idea for you right now to put this video on pause, walk away from the computer, and think on your own how you will marry this information, this hint over here, with our first hint, and how will you splice the divide and conquer problem solving approach into that distinct proof of the Heron's formula. Well, this version of a proof of the Heron's formula will be very short and very sweet, precisely because of the power of everything divide and conquer problem solving approach, our ability to fish out from our personal web of mathematical knowledge this here wonderful theorem that if three real numbers x, y, and z sum to pi, then the sum of the values of the respective trigonometric functions of tangent will be equal to the product of these very same values. The whole in this case will be our triangle ABC again, but the parts, the smaller and simpler primitive parts, will be this time not 3, but actually how many? Come on, guys, think on your feet, think fast if you want a credit for this problem. 1, 2, 3, 4, 5, 6. The smaller and simpler primitive parts in this case will be 6 smaller triangles that, again, the triangles that we saw when we were proving this result in our one of the very first segments of this episode. And what does that mean? Well, using these 6 smaller and simpler primitive parts, 6 triangles, we show that, for example, the triangle CGO is exactly congruent to the triangle CFO. That much we can prove. Likewise, we can prove that the triangles AOD and AOF are congruent. Likewise, the triangles BDO and BGO, pairwise, these two triangles are congruent. Again, they are congruent because of the way in which the incenter of our parent triangle was constructed. Angular bisectors, these angles are equal. These lengths over here are equal. Consequently, the angles, the interior angles, the magnitudes of the interior angles are also equal by, for example, what is it? Side, angle, side. These triangles are congruent. But what does that mean? That means that the magnitude of this angle is the same as the magnitude of this angle. That also means that the magnitude of this angle is the same as this angle. And that means that the magnitude of this angle is exactly the same as the magnitude of this angle. You see? And now we write what? This will be x. For example, this angle over here will be y. And this angle over here, let me write it down here. This angle over here will be z. Now, what do we have? Well, x plus x, 2x, y plus y, 2y, and then z plus z, 2z, equal to exactly 2 pi. In other words, if we place ourselves into the incenter of the parent Euclidean triangle ABC this way and point ourselves, for example, at the point F over here, this point, and then we walk counterclockwise and make one complete revolution, we will sweep what? The complete angle 2 pi. But that complete angle can be the composite quantity, again, can be represented as the sum of the angles FOC and COG. These angles are the same. We call these guys Y. The angles, what is this? GOB and DOB. So we call these angles Z. Pairwise, these angles are the same. And the angles AOD and AOF. These angles, we call them X. They're pairwise the same. They're equal. And this is how this sum comes about. Divide this equation through by 2. Precisely get the premise of the theorem over here. If P then Q, p holds, x plus y plus z equals pi. And what do we do now? Now the only thing that's left is to hijack the results that we proved previously. Remember that in the previous segments we proved that this distance right here is p minus a, and I used the green chalk the other time. This distance right here is p minus c. And all we have to do now is, yes, we modernize our proof, and we use the trigonometric function of tangent using the material what? The length of the in radius r and the length of the tangent line segment over here. For the tangent of the angle, which one? X. For the tangent of the angle AOD, what do we have? We have P minus A over R. You see, the length of this side divided by the length of this side for the tangent of this angle. For the tangent of the angle Z, or for the tangent of the angle BOD, what do we have? We have P minus B plus P minus B over R. And what do we have for the tangent of the angle, this guy, Y, for example, the tangent of the angle COG? It's the length of the opposite side, P minus C, divided by the length of the adjacent side, plus P minus C over R. This is our tangents, trigonometric functions of tangents. And in this miraculous case, this sum is equal to the product of the same things. P minus A, P minus B, P minus C over R times R times R. Isn't that wonderful? One copy of R cancels out. And what do we have? Well, P plus P plus P will be 3P minus A minus B minus C minus 2P comes out to P, and this is times R squared equals to our product P minus A, P minus B, P minus C. You see, that is how straightforward that is. 3 copies of the semi-perimeter, P minus 2 copies, minus A, minus B, minus C, so minus the sum of the lengths of the side, twice the semi-perimeter, minus 2P, 1P. R squared comes from the denominator on the right-hand side of the equal sign into the numerator, so to speak, of the left-hand side, here, this guy, and our product of 3 terms. But what is R squared? R squared is P times S squared over P squared. And what do we have now? 1 copy of P, 1 copy of P, equal to our product. So now you understand what happens if I move this guy from P to here. P times, again, our favorite product. P minus A, P minus B, P minus C. Heron's formula proved, all courtesy of what? The divide and conquer problem solving approach and our ability. Remember, mathematics is first and foremost the play of thought. The a mathematical thought is the first class citizens in mathematics. Our idea to generate, happy idea to generate this thought and fish out from our web of mathematical knowledge the theorem which says that if the magnitudes of 3 real numbers x, y, and z sum to pi, then the relationship for the values of the trigonometric function of tangent evaluated at these arguments holds as shown over there, and everything else is followed. Again, divide and conquer over here was used which way? We took our given Euclidean triangle ABC to be the whole. We partitioned it into 6 smaller and simpler primitive parts. Again, remember, you can always write it down. The triangle ABC equals the union of the 6 smaller triangles. The solution of each and every one amounted to what? The solution of each smaller and simpler primitive part amounted here in this case to writing down precisely this for the value of the trigonometric function of tangent. This was the solution. And what was the combination? Well, the combination of find a way to combine the solutions of the whole into a solution, find a way to combine the solutions of the parts, of all the primitive parts, into a solution of the whole, came precisely from this theorem right here. This was our way to combine the solution of all the primitive parts into a solution of the whole, and this is it. Again, this is just one example, and altogether we discussed two distinct proofs of the Heron formula using the divide and conquer problem solving approach, but you guys should not stop here. You should try your hand at constructing your own proofs that are different from the ones that we showed over here. Again, don't be shy, share your ideas with us in the comment section. And right now, we're done with the mathematical problem S2M41, and we will move on to a new challenge next. Our next challenge, the mathematical problem S2M42, may come across as scary and difficult at first blush, but if you have a good organic understanding of geometry, that this problem is really of kindergarten variety. It's not that scary, it's not that difficult. But in this problem, we're given a unit hyperbola, 1 over x. And we know that graphically, in grown-up mathematics, a function and its graph are two different mathematical objects. We should not confuse the two. So a unit hyperbola given as, for example, which way I should write it, as, for example, in the analytic geometry style, it will be y times x equals 1. This will be our unit hyperbola. But in this problem, we're told that the point Q belongs to the, let's say, positive branch of the unit, of the graph of the unit hyperbola. I showed it over here. That branch of the graph of the unit hyperbola is located in the first quadrant. And we're told that the point P is located on the negative branch of the graph of the unit hyperbola. That branch of the graph of that function is located in the third quadrant. I, in some sense, abuse the notation over here, but you guys understand. The point Q is on the positive branch of the graph of the unit hyperbola, and the point P is on the negative branch of the graph of the unit hyperbola. And then what we do is this. We project the point Q onto the x-axis to obtain the point QX. This is the x-axis projection of the point Q. And then we project orthogonally the point Q onto the y-axis to obtain the point QY. QY is the orthogonal projection of the point Q onto the y-axis. QX, QY. The same thing exactly happens to the point P. We project the point P orthogonally on the x-axis in order to obtain the point PX. And we project the point P orthogonally onto the y-axis in order to obtain the point PY. Now, we listen carefully. What happens next is this. We connect the points Q and then PX and PY. I try to show, I drew this triangle in green. I'm not sure if you guys can see it that well, but this is in green, the triangle Q, PX, PY. So far, so good. That is easy to remember. Two coordinates or two vertices of this triangle come from the point P, so to speak, PX and PY, and the other vertex comes from the point Q. Likewise, we grab the point P, and with that point P as one of the vertices, we construct the following triangle: P, QY, QX, or PQX, QY. These two triangles. And apparently the author of this problem is somehow sure that the areas, this time I designated with the uppercase A, just because for my brain it's easier. Area A, there you go, area of these two triangles, is apparently one and the same. In other words, your challenge, should you choose to accept it, your mission, should you choose to accept it, is to generate a convincing proof, a convincing line of reasoning, using the divide and conquer problem solving approach. This is a hint that the area of the planar triangle QPXPY, area of the triangle QPXPY, is exactly the same as the area of the planar triangle PQXQY, If you have any questions about the problem statement, don't hesitate, don't be shy, use the comments in the comments section. But this is the challenge. Again, this problem may seem very difficult, but this is nothing beyond middle school. Literally, this is middle school curriculum if you know about the divide and conquer problem solving approach. Again, the challenge is right now I'm going over the details of how the divide and conquer problem solving approach works very slowly, very methodically, very thoroughly, because this is how things work when you learn new things. Once you learn them, you will zip through problems in an instance. You will not even think about it. This will be unconscious, and by the time you cross the finish line, you'll look around and you'll, oh yeah, gee, I solved the problem. Divide and conquer. Hooray. So here again, think about this problem. See where, first of all, as another hint for you guys, there is a very convenient, very elegant, and very straightforward hole hiding somewhere in this graph. Again, remember, a function in mathematics is a totally different object from a graph of that function. So here again, I hijacked the notation a little bit, but you understand Q on the positive branch, P on the negative branch of the graph of the unit hyperbola. Go at it, and if you are a mathematically inclined thinker, you will of course think of a case when the points P and Q are located actually on one and the same branch. Think about this. When the points P and Q, once you solve this problem, think about the situation when the points P and Q are located on the same branch. Which one doesn't matter? Same positive branch or the same negative branch of the graph of the unit hyperbola. Generate a convincing proof. See how it works. Good luck to you. This is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will share with you my solution of the mathematical problem S2M42.